Welcome back to the Rad Lab Podcast. Today we have a special guest, Dr. Jennifer Laaser. She hails from University of Pittsburgh, where she is associate.
I just got promoted to associate professor.
Congratulations to associate.
Dyed my hair purple in celebration.
There you go. Awesome. Amazing. Hopefully I can join those ranks in a few years. Some highlights for Dr. Laaser. She has won the NSF Career in 2019. She has been awarded a AAAS Mass Media Fellowship, and she has won the Tina and David Bellett Teaching Excellence Award at University of Pittsburgh. So tons of accolades. We can get into tons more, but those are some of the highlights. And so hopefully that will lead us into some of the conversations we're going to have later. And some of those awards definitely highlight some of the diverse background that Dr. Laaser has had. So with every guest, we try to start kind of from the beginning, and even you can go as far back as you would like. But I often like to see, okay, where did you get started? Where are you from? And we can start from there.
Sounds good. Well, thanks so much for having me. It's a pleasure to be here. It's hard to say when I got started in chemistry specifically, but I think I've been a scientist or somewhere in the STEM fields for pretty much as long as I can remember. So I grew up in Palo Alto, California, and my dad is a mathematician/computer scientist, and he was always giving me little math puzzles to play with growing up. And I really enjoyed the logical thinking that I got to engage in. And so that kind of carried over into just getting really excited about my science classes in middle school and high school particularly. And so, I knew that I wanted to do something in the sciences just because, I got so excited about things like getting to go on a field trip to the Stanford Linear Accelerator Center and just seeing this giant particle physics experiment that you could literally walk around and then had to hide behind lead blocks to protect yourself from the radiation of the experiments. It was just it just made me really happy, and so I knew I wanted to do something in the sciences, but I didn't really know what I wanted to do in the sciences when I went to college, and so I applied to college, and I think I said I wanted to be a physics major. I don't even remember, but I got to college and I sort of just started taking courses across the sciences to satisfy all of my science prerequisites. And one of those courses was a general chemistry course taught by a guy named Mark Johnson. And he did this thing of offering extra credit assignments where he said the rule was you couldn't talk to the TAs, you couldn't talk to the other students, you could only talk about them with him if you needed help. And so you had to go to his office hours to ask questions if you needed help. And so, for any students listening, really do go to your professor's office hours. They actually want you to come ask questions. And I think I didn't understand that at the time, but we really do want you to come ask questions. But anyway, I started going to his office hours, and he would wrap up his office hours and he'd say, okay, well, office hours are done. I'm heading down to the lab now. You guys can come if you want. And so I just kind of traipsed down to his research lab with him after office hours. And the first time I walked in, this was a lab that did gas phase spectroscopy. And so they had these giant vacuum chambers where they were doing these gas phase spectroscopy experiments. And they had these lasers that were firing at 10 hertz. And so you could walk into the lab and actually hear the lasers firing, pew, 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 10 hertz, 10 times a second. And I think I just walked into that lab and I just had this feeling of like, this is my place, right? And I think that is when I became a chemist. And so, I ended up majoring in chemistry. I did research in that research lab as an undergraduate. I went to grad school in chemistry where I did my PhD in ultrafast laser spectroscopy. And, along the way, I realized that I had learned a lot of how to measure things and how to build cool instrumentation to measure things, but I didn't really know how to make the interesting things to measure. And so I decided when I finished my PhD that I wanted to go on to a postdoctoral position where I'd have to learn to make things. And so I ended up deciding to do a postdoc in polymer chemistry and polymer physics at the University of Minnesota. And I really just fell in love with it. It's so much fun to make things that I can hold in my hand and feel how changes that I've made at the chemical level affect the bulk physical properties of the material, like how stretchy it is. I can make things and poke them and see how changes that I've made change their response when I poke them. And I just find that so much fun. So I've just continued with that ever since I started my postdoc. And so that's kind of been my path to becoming the chemist that I am now. And I think that what being a chemist means to me has changed a lot over that time. When I was an undergraduate, I was really into we're going to do the instrumentation, we're going to do the laser spectroscopy, we're going to build new experiments with lasers. And now I'm much more in the land of making things from small molecule reagents that I can buy from Sigma Aldrich, but then turn into this thing I can hold in my hands and do something with. And I find that really rewarding, and I find it really cool that is all chemistry.
Yeah, I think that's the great point about chemistry. Chemistry, I feel like people have they have a certain perception of chemistry, and it's very rudimentary. They don't know how far it expands. It can be, designing instrumentation and, or making the things to measure on that instrumentation, or both, and all these things. And you've been able to combine both of those things. And I think that's an amazing place to be.
Yeah.
So to go back a little bit, just to talk about grad school, to touch on it just a little bit, the question I like to ask everyone when they come on here, because we have a lot of students that are thinking about grad school, and what kind of skills they're always trying to figure out, what do they need or how can they be prepared for grad school. So if you had to go back, get your PhD all over again, and you could only take one skill with you, what would that one skill be?
So I think that if I could only take one skill with me, it would be being able to maintain a sense of the big picture of a scientific problem, even while I'm down in the weeds of trying to solve the little minutia that I need to solve to get my current experiment done. And I think that that's something that was really hard to see as important as a graduate student, because as a graduate student, my PhD advisor was really directing a lot of what I was working on. It's not to say I didn't have any direction, right? I made a lot of decisions about which kind of directions we were gonna follow to solve the problem that we were trying to work on. But I didn't really have to think as much about the big picture of what I was doing, because that was being given to me. And now, as a advisor and PI myself, thinking about that big picture is a really important part of what I do. And looking from my current perspective, I see that it's actually something that a lot of grad students really struggle with, but they would be much stronger if they were able to keep that big picture in mind. And so, when you finish a PhD, you will have made a contribution in a very, very small area of science, right? A PhD is a very, very focused research problem. There's, if you haven't ever seen it, there's this cartoon or graphic about what a PhD is, and it's kind of representing the extent of human knowledge as a circle. And as a high school student, you learn a little bit of it. As a college student, you learn a little bit more. Your circle gets bigger. As a master's student, you start bumping off in a specific direction. And then as a PhD student, you're pushing at the boundary of human knowledge. And then at the end, by the time you finish your PhD, you've kind of bumped that boundary outward a little bit. But I think that as a PhD student, it's very easy to get so down in the details of what you're doing day to day that you lose sight of why you're doing it, right? Not only why you're doing it for yourself, maybe you want a specific job that it'll be easier to get once you have a PhD, but also why the science is important for science and for society. And so I think that just being able to maintain that big picture and use that both to help keep yourself motivated, but also to better frame your work when you're writing about it, when you're putting it together in your PhD thesis, when you're reading new papers, think about how they fit into that bigger picture rather than just the minutia that you're working on day to day. I think that that's something that really makes strong PhD students stand out, and it's something that I would want to take back with me.
Yeah, no, I think that's an amazing point. I think being able to have that bigger picture it just sets the stage for everything else that you do. And for my students, I always tell them the question you should always be able to answer is why. Mm-hmm. You should be able to answer why. And so I almost pop quiz them on why are we doing this?
Yeah.
And, sometimes they can't give you an answer, so we talk about it. And it's one of the most important questions, but it should be the easiest because the chemistry you're trying to do to solve a problem is actually the hard question that you try to answer, but you should always be able to answer why.
Yeah, yeah.
And so I think that's an amazing piece of information for any student, that you should always know why. So from your graduate school to your postdoc, you decided to make a little bit of a change. Mm-hmm. So can you talk a little bit more about what that change was like and what were the difficulties, or was it easy? Like how did that play out?
Yeah, so it was honestly a little bit scary to go from a PhD where I knew all the techniques, I knew how to work with optics, I knew how to write code that would control my detectors and all that, to a postdoc where I was going to really have to, work with chemicals and make things. I like to joke, but it's not really that much of a joke, that when I started my postdoc in polymer science, I had only made one polymer before in my life, and that had been unintentionally in my sophomore organic lab. We were supposed to be doing a Diels-Alder reaction, and instead of the nice crystalline small molecule product I was supposed to get, I got a brown polymerized sludge at the bottom of my reaction flask. So that maybe didn't make me so confident that I could actually do that type of chemistry and do it well. But I was lucky to find a postdoc advisor who was willing to take a chance on me and willing to give me the time to learn those things. And it wasn't smooth sailing. When I started my postdoc, one of the very first reactions I did was I polymerized styrene, to make polystyrene. And for those of you who have never done any polymer chemistry, this is like the easiest polymerization ever. This is the one that we do in day one of an undergraduate polymer chemistry lab. And it really should just be, you mix the stuff together, you heat it up, and you come back a couple of hours later and you have polymer. Well, in my first week of my postdoc, maybe my second week, I managed to screw it up. I set this reaction up, and it was one that I was supposed to do in an air-free environment. And so I had, carefully removed all the oxygen from my reaction flask and covered my reaction flask with a septum. And then I started heating it, and the reaction pressurized enough that it popped the septum off the top of the flask, exposed the entire thing to oxygen, and killed the polymerization, right? And then I accidentally dumped the waste from that reaction mixture into a fresh bottle of solvent that I was convinced my postdoc advisor was going to fire me. I didn't ever tell him about that, so maybe he shouldn't listen to this podcast. But it was really rough because I honestly didn't have the wet lab skills to be able to just jump in and start doing that. But luckily there was another postdoc in the lab who kind of took me under her wing and started walking me through how to do a lot of these things correctly. And, within about 3 or 4 months, I was routinely making these materials that I needed to make. And, about 6 months into my postdoc, I was having a lot of trouble with one of my syntheses, and I realized that it was because there was a side reaction that was happening that we actually couldn't suppress. And so I showed up in my postdoc advisor's office and I said, well, you told me to make this polymer using this method, and it turns out we can't because, and I laid out the chemical problems that were preventing it. And I said, so instead, I think that we can achieve the same, goal in terms of our overall project if we make this other version of this polymer instead, which will avoid this problem because, and he just sort of looked at me and says, sounds like you've got it all figured out, right? And I think that was a point at which I said, day to day, I haven't seen this progress in learning these skills that I didn't have before, but over 4 to 6 months, that day-to-day progress has built up into actually a lot of polymer chemistry knowledge, both practical and the kind that you kind of sketch out with a pen and paper when you're drawing structures and thinking about mechanisms. And so I think that it was a transition that at the time, like in the midst of it, felt almost impossible. Clearly I decided to do it, so I didn't think it was actually impossible, but it sort of felt that way sometimes. But in retrospect, it was one of those things that just being in an environment where I was given the space to play and given the space to make mistakes, and then to learn from those mistakes, it turned out to be a really fantastic opportunity, because now I know a lot about polymer chemistry that I don't think I would really understand in the same way if I had just been kind of spoon-fed it, right? Yeah. And so it ended up working out really well, and I'm so glad that my postdoc advisor gave me that opportunity, and it's clearly stuck with me because I really like it, and I've continued to do this type of work in my own lab at Pitt.
Yeah, no, I think you're a walking billboard for what I've been trying to tell students for a long time. And it's, people, you go get your PhD and you kind of fall into a lane, and then people like to be comfortable. They like being in that lane. Mm-hmm. But I think, when you go off to do a postdoc, it's like the perfect time to try something new.
Yeah. And
it could open up a whole nother avenue for you and inform you to do something different that you thought you may not have thought about.
Yeah.
And I think that's an amazing thing for anyone to do.
Well, I think that's, worth thinking about, not even just at the transition from a PhD to a postdoc, but also at the transition from an undergraduate degree to a PhD. So, I have a lot of undergraduates who work with me at Pitt, or who take my classes at Pitt, and who are thinking about going to graduate school. And they worry about, can I do something different in graduate school than I did as an undergrad? And yes, absolutely, you can, right? Going into graduate school, like we don't typically expect students to know all the things. Otherwise, why would they be doing a graduate degree, right? Like, you're supposed to be learning through the course of that degree. And so, as an undergrad, you learn how to learn at the undergraduate level, and then you take that to your PhD and you can apply it to a different area, right? The same thing happens when you go from a PhD to either a postdoc or, a position in a company or something like that, that you have learned all of these skills about how to think about a scientific problem, how to design experiments, etc. And you might go do exactly the same thing that you did in your PhD in that next position, but those skills are transferable across a much wider range of topics. And yeah, you might have to learn a new instrumental technique or a new synthetic technique, or in my case, learn how to do synthesis entirely. But you have learned how to learn those things. And I think that, it's important to recognize that those skills are transferable, and that you're not stuck doing just the one thing that you've chosen to do right now.
Yeah.
Right?
Great point. I didn't even think about that. I'm stuck in the other realm. But we get a lot of students that they did this thing in their undergrad and they think they have to keep doing it. Mm-hmm. And it's hard to break that cycle, because especially for me, not a lot of students get exposed to radiochemistry. Mm-hmm. And so it's hard to convince these, people who want to do analytical or organic, that's what they did in their undergrad, to convince them, I think you should do radiochemistry, and try to tell them why it's cool, because they're kind of already set in their ways.
Yeah.
I think more students need to be more flexible, and it's this is the time to try different things. And when I went on to my graduate school, I thought I was going to do organic. Mm-hmm. And I didn't even know what radiochemistry was. And then I was like, I don't like organic on this level. And so I looked across the hall and I was like, that stuff looks like it's glowing. That's kind of cool. And so I went across the hall and I was like, let's try this, and I made that switch. And so even if you get there and you find out that it's not what you like, you can still switch. Mm-hmm. You can still change.
Yeah.
recognizing that it's not what you want something else, the quicker you can do that, I think the better. But, it's sometimes hard, to make that switch. It's never too late to change and do something a little bit different.
Yeah.
So you finished up your postdoc, you have all these new skills, right? So how did the transition from postdoc to a professor? So tell us a little about your research and what you're doing now.
So in my lab at Pitt, we really like to think about the connections between molecular scale chemistry and the bulk properties of polymer materials. And so we kind of do that in two main areas. We make a lot of charged polymer systems where we're putting charged functional groups onto the polymer chains. And we're thinking about how the chemistry of those charged functional groups and other chemical functionalities on the polymers affect things like the phase behavior of those polymers when we put them in solution, their viscosity, their elasticity. Those are things we don't usually think about as chemists. But when you start thinking about the materials applications of a polymer, how liquid-like or how stretchy it is, those are things that really start to matter. And so we do a lot of charged polymer systems that are very inspired by the proteins that undergo liquid-liquid phase separation in cells. We also do a lot of charged polymer systems that we're looking at for CO2 separations membranes for carbon capture. And then the other half of my lab thinks a lot about polymer networks. So polymer chains, I like to sort of draw them as just molecules that look kind of like spaghetti. But if we imagine stapling together pieces of spaghetti, where we can form a cross-linked polymer network, and those materials tend to have a lot of really interesting elastic properties, for example. And so we are really interested in thinking about, okay, if I stretch a polymer network, how is that macroscopic force that I'm applying felt at the molecular scale? Like, what are the molecules in that network feeling as I stretch my rubber band, for example? And so one of the tools that we use to investigate that is called mechanochemistry. And so this is a really fun field of chemistry where you actually use force to drive chemical reactions. And so we make a lot of materials that turn purple when you pull on them, and that's just okay, purple's my favorite color, but I just think that's really fun. But so across all of these things, we're really thinking about how we can use our skills as chemists to change the chemical functionalities of a polymer, or to put in an interesting chemical response in a polymer, and then connect that to either the bulk properties that we feel when we poke the polymer, or to the macroscopic forces and deformations that we apply, and how those are kind of transduced to the molecular scale.
Oh, that's really cool. Yeah. Could you explain a little bit more about mechanochemistry?
Yeah.
This is my first time hearing mechanochemistry, so I'm excited.
Yeah, so, mechanochemistry is really just force-driven chemistry, okay? And so if you think about a chemical bond, right, we tend to think about that chemical bond, we can break it by, for example, applying heat, right? But another way you can break a chemical bond is literally by pulling the atoms apart from each other. And so that is mechanochemistry, okay? Is literally pulling the chemical bond apart. And so, this is in polymers, it's a phenomenon that I think was actually first observed in processing of rubbers. I forget when this was reported, but if you take a high molecular weight polymer, so a polymer where the chains are really long, and you start shearing it or rolling it, you start to see the viscosity of the material drop, and that's because the chains are actually breaking and getting shorter. And most polymer chains have just a string of carbon-carbon bonds in the polymer backbone. And so if your chains are getting shorter, you're breaking carbon-carbon bonds, right? And so that's doing mechanochemistry. And so that's what I think folks in the field now would refer to as destructive mechanochemistry. But in the last 15-ish years, there's been this realization that you can use force to drive productive chemical reactions, i.e. you pull on a bond and you cause a chemical change that does something useful, right? And so one of the kind of ones that we use all the time is this molecule called spiropyran, that if you pull on it, you can break a carbon-oxygen bond, and it causes the molecule to rearrange itself or isomerize into a form that is colored. And so you can use a color change in your material to kind of read out the force that that molecule felt at the molecular scale. But there have also been, force-responsive molecules reported that, for example, release a pharmaceutical compound or something that could be used as a therapeutic. There are mechanophores that, when you break the bonds, you generate radicals that can then initiate a new polymerization reaction to help a material self-heal. So there's a lot of really cool stuff that you can do by applying force to chemical bonds, right? But the challenge is that molecules are small, really, really small. And so it's not like we can easily just go in with a pair of really tiny tweezers and grab onto the molecules and pull. And so it turns out that polymer chains are a really, really useful handle for pulling on molecules, because if you can attach the polymer chains at the points you want to pull on, then if you can kind of attach that into a network or put it in a solution where you can sonicate it and generate chain stretching, then you can sort of use those polymer chains to pull on your molecule and drive this productive chemistry. So it's a really fun field, and it's, I kind of got into it because there's been a lot of work on developing new force-responsive molecules that do useful things, but the efficiencies of activating those molecules tend to be really low. And if you're putting in all this work to make this fancy molecule that's going to do this useful thing, you don't want to only be able to use 0.5% of it, right? And so we try to bring our perspective as physical polymer chemists, or we'd say polymer physicists, to understand how we can kind of design the surrounding polymer material to make that process more efficient. So
wow, that's so cool.
It's really fun.
That's amazing.
I wish I was this is a podcast, so I can't just show you this, but I have a video of one of these things that's a transparent sample, and you pull on it and it literally just turns blue on the video.
Post it on your.
It's really cool.
So Dr. Laaser has a YouTube channel. We were going to see if we could shoehorn this in. So please tell us, what is your YouTube channel handle?
Yeah, so my YouTube channel is ChemProf Jenny, and it currently, I will say, only has 3 videos on it. But I have a long list of additional videos I need to make, and I just need to get around to doing it. But, time management is one of the biggest challenges of being a professor, honestly. You asked me about the transition to being a professor. Time management is one of the hardest things, just because the demands change so much. But yeah, I try to put together videos with advice for students. So I think the videos that I have up right now are one on writing statements of purpose for grad school, one on deciding whether you should go to grad school, and I think the other one is on finding undergraduate research positions. So I'm hoping I'll get back to that sometime soon.
You should.
But
you should post that video of your polymer on short. Put it as a short.
I could do that. Right. You're right. Okay.
That'd be amazing. I'm looking forward to it. I'm looking forward to that video to get posted. I can't wait to see it. So I will link her YouTube channel in the description. So if you would like to go check this video out, please check it out, and also learn about these other great topics that she has videos on. I think I'm excited. I get to hear your talk. So is the video in the talk later?
No, I'm not talking about that topic today.
Now you got me all excited.
Yeah, I know. I'm sorry.
That's okay.
I'm sorry.
So when you're talking about putting these polymeric handles, so are you inserting these small molecules into this polymer? So you're growing one handle and then inserting it and then growing it off the other end?
Yeah, so usually we're actually putting 2 initiation sites on the small molecule and then growing the polymer off in
Makes
both
way
directions.
more sense than what I just said, yes.
You can do it the other way too, though. It just every time you have to couple on a new molecule, you have some chains that don't keep going. And so then you end up with messy distributions of polymer chain lengths.
Gotcha.
So yeah, we do tend to just grow symmetrically off the same molecule.
That's awesome.
Yeah, it's fun.
How does it make? Maybe we're getting too much of the weeds here, but I'm trying to wrap my head around some of it. So you pull on this chain, and you said that it could make some another small molecule.
Uh-huh.
So it reorganizes itself and then comes and then releases? How how does that?
Yeah, so I will say we don't work with the mechanophores that do those release processes, so I can kind of only give you the high level picture of that.
Fine.
But yeah, it's basically you kind of distort the molecule enough that bonding to this thing that it's trying to release is no longer favorable, and so then it breaks away, right? And oftentimes people do these experiments in solution, and so they use a sonicator to drive the chain extension. And so a sonicator is basically really, really powerful ultrasound. And if you use a sonicator, you end up having this process called cavitation happen in your solvent. And so you end up with these voids that open up in the solvent and then they collapse really fast. And when they collapse, they drag a bunch of surrounding solvent in. And as that solvent flows, it stretches the polymer chains. And so you can imagine that if you're doing if you have a mechanophore in the middle of your polymer chain that's going to release a small molecule, that small molecule is then just going to be released into solution, right? And so then it could go do something useful. Now, a lot of times people are trying to make these mechanophores that release small molecules for use in drug delivery, for example. And so there, you have to worry about sonication also tends to do bad things to biological tissue, and so there's some tricks that people play with that. We're much more interested in my lab in the kind of bulk materials. So how can I make a piece of hydrogel that you could insert in a place where a thing needs to be delivered, and so then you'll activate your mechanophores, release the thing, and then it'll be able to diffuse to where it's needed. We're not really trying to do those delivery applications ourselves. We're really trying more to understand just the fundamental, how does the structure of the polymer and the polymer network impact this force-driven activation process. But yeah, those are the kinds of things that folks are interested in doing with those.
Oh, that's amazing. I think, oh man, now I got to dive into this a little bit more. But so speaking of diving in, I guess, into this type of field, so papers that you put out, it's almost like a child, right? So how can you pick your favorite child, right? But I'm going to ask you to do that. And if you can pick multiple. We've already had someone kind of cheat the system, so
yeah.
we'll let you pick a couple if you need to. But so if we're going to pick a couple, I'll pick one that you think represents maybe you the best, and then maybe pick one that you think it represents maybe you and your group as a whole the best.
Yeah. So I'll give you one from each of those kind of subfields that okay. I was telling you about. So with our charged polymers work, I think, maybe it's just because it's the most recent, but I'm really excited about a paper that we just had accepted to macromolecules. So it's not actually published yet, but hopefully by the time this podcast comes out, it will be. So I can give you the link. But we've been working on these charged polymer systems that are, as I mentioned earlier, inspired by biological molecules that undergo liquid-liquid phase separation. And a lot of the proteins and biological molecules that do this process have aromatic rings in them. And it turns out that a lot of the kind of model systems that people in the polymers field use also have aromatic rings in them. If you've taken a biochemistry or biophysics course, you've probably heard about cation pi interactions and the fact that interactions between cationic functional groups and aromatic rings can be really important for stabilizing proteins. Well, it turns out that in the polyelectrolyte complexes field, people just kind of don't worry about that. They just say, oh, it's all just the charge interactions. And I'm overstating a little bit. There's some people who've thought about this, but it's not something that we've really given a lot of weight to as a field. And so we came up with a really simple way to look for the impact of cation pi interactions in these materials. And that is basically just testing the phase behavior and the viscoelasticity of the materials in the presence of salts with different cation pi binding strengths. And so if you put your material into a salt that has a salt solution where the salt has a strong cation pi binding strength, you'd expect it to kind of like outcompete interactions between the polymer chains. Whereas if you have a weak cation pi binding strength, it probably won't outcompete those interactions as well. And so those should result in differences in the properties of the material. And if you do that with a polymer that does not have any aromatic groups, they shouldn't really care what the cation is. And so we just had this paper accepted where we showed using one of these canonical polyelectrolyte systems that people have been using for like literally more than a decade. We showed that when you do this experiment, they care about what the cation is. And I think that means that we should, really not be ignoring cation pi interactions in these systems, and that we should be thinking about how they're affecting both the stability of the complexes, but also their physical properties like their viscosity and their elasticity. So I really like that paper because it is such a simple technique for looking for this signature of cation pi interactions. But I'm really proud of it because we kind of thought outside the box in terms of what our community was doing and figured out how to do this simple test that hopefully other people will be able to apply to other systems as well. So that one's one I'm really excited about, and it really was just accepted like earlier this week. So I'm very excited about it right now. But then I would say probably the other paper I would highlight is one of our mechanochemistry papers. And so I didn't really say this earlier, but the polymers we make are usually actually not covalently cross-linked polymers, but they're ones that self-assemble into a network. So we make these polymers called triblock elastomers that have two different types of polymer linked covalently together. And then those two different types of polymers don't want to mix, but they also can't totally phase separate from each other because they're covalently linked. And so instead they self-assemble into these structures with kind of like tens of nanometers length scales. And so through a combination of both experiments and computational models, we showed that if you mix chains with different lengths in these materials, then those chains with different lengths don't all feel force in the same way. And so we showed that the short chains activate way more than the longer chains. And that paper, I think, just is also very representative of the way I like to do science, because we really worked hard to find a way that we could kind of make multiple samples that were directly comparable to each other, but then systematically change just where this force-responsive molecule was placed in the material, and showed that there was a really big difference in its response depending on which subpopulation of the chains we put it in. And then we also worked with a friend of mine at the University of Illinois, Antonia Stott, to do these computational models and be able to put together a really nice visual picture of why this process was happening. And so that paper was in Macro Letters a couple of years ago. And it's very near and dear to my heart because it was really fun to put together, and it was honestly a really fun collaboration to work on too. And collaboration is something that I take a lot of joy in, especially when I'm working with collaborators that I collaborate well with and enjoy working with. And so it's just one that makes me happy. Yeah.
This podcast will definitely come out after that paper has come out. It takes me a little bit, probably longer than I want to admit, to edit these. But please send me those links, and they'll be in the description. And please check them out. I'm going to check them out. I think those sound amazing. So please check those out. So before we started, chatting on the podcast, you mentioned that your career kind of took a little bit of a turn. Mm-hmm. Like chemistry, it wasn't maybe always about maybe being a professor and things like that. So tell me a little bit about, that path, I guess.
Yeah. So, I think this is a really important thing to talk about, right? Because I think a lot of times we look at people who are, further ahead in their careers and we go, oh, they must have just had it figured out from the beginning. And that's not really true, right? And I think it's important to recognize that like what we think we might want to do can change several times over the course of our career. And so, when I started my PhD, I sort of said, yeah, maybe I'll be a professor, because I didn't really know anything. I had basically been a student my entire life. I hadn't really done any exploration of other career opportunities. And so I just saw these people who were doing stuff that I thought was interesting. And I said, yeah, sure, that's what I want to be. Anytime anybody asked me what I wanted to do, I said, yeah, I want to be a professor. And, over the course of my PhD, I sort of stuck with that, but I also, toward the end, I was just feeling really burnt out. And I think that that's a really common experience among PhD students, right? A PhD is a long and difficult process, and it's really rewarding, but it's also it's hard, right? And you go through a lot of times when your experiments aren't working, and when you do finally get them to work, that's really exciting. But it's also there are long stretches of time when it's just man, I just keep doing the same thing over and over, and I'm just not getting anywhere with this. And so, yeah, toward the end of my PhD, I was just kind of feeling sort of burnt out. And I started thinking, maybe this isn't what I want to do. And so for a number of reasons, I got interested in science writing. And so I did some writing for the student newspaper at the University of Wisconsin, where I got to go interview scientists in other departments and write about their research work for the student newspaper. And then one thing led to another, and I ended up applying for the AAAS Mass Media Fellowship in my last year of graduate school. And so the AAAS Mass Media Fellowship is this fellowship that's run by the American Association for the Advancement of Science. And what they try to do is they try to take science students, primarily PhD students, although they do also take some undergrads, and place them in newsrooms of major news organizations around the country for about 10 weeks over the summer. And I was lucky enough to get one of these fellowships. And so I ended up going and spending a summer working at the Milwaukee Journal-Sentinel as a science writer. I was sort of went into this saying, maybe this is what I want to do, right? And I think what I came away with is, no, that's not what I want, not what I want to do. I think that, I found that I'm really bad at cold calling sources. I find it really, really stressful, and that was not something I wanted to have to do. It's still something I have to learn to do. Calling program officers is still very stressful for me when I have to talk about grant applications and things, but it wasn't what I wanted to be part of my day-to-day life. And I think it's also a position where there's not a lot of job security, and I think those are things that I just started to see while I was actually working in that field for a summer. And so, that helped me say, okay, that's not what I want to do. Although I did bring a lot back from that experience that has informed the way I communicate about science and the way I write about science now. So we can come back to that later. But I then went and started my postdoc, and I was still kind of on the fence, what do I want to do? And during my postdoc, I was lucky enough to be in an environment where there were a lot of connections to folks who were working in industry. And so this was both through official relationships between the university and a number of companies, but also just, alumni of the department that I was working in would come back and give talks and things like that. And so I got to connect with a lot of folks who were working in the types of industry positions that I might be eligible for or that I might be competitive for with my, by then, polymer chemistry experience. And so I did a lot of sort of informational interviews with people who were working in those positions. And so informational interviews are a really, really powerful way to explore different career paths, even as you're still a student. And so basically you ask somebody who's in a position that you think you might be interested in to sit down with you for maybe 30 minutes or so and just ask them about their career path, how they got to where they are, what their day-to-day is like, what their advancement pathway looks like, why they chose to pursue the career that they're pursuing. And if you are on the fence at all about what you want to do, I highly recommend trying to connect with some people that you can do informational interviews with. The point is not to ask for a job out of an informational interview. It's really to gather information about a potential career path. And so I did informational interviews with a number of folks that were kind of working in industry positions. And what I came away with was that I think I probably could be really happy doing research in industry, especially if I kind of found the right company to work at. But that for me, the piece that I would really miss is the working with students and the teaching and mentoring aspects. And that's not to say that people who are working in industry, like the people I was talking with, weren't doing some mentoring. It just wasn't a core part of their job in the same way that it is as an academic or as a faculty member. And I think that was the point at which I realized that the teaching and mentoring piece was something that I really wanted to be doing. And so does it drive me bonkers sometimes? Yes. But it's also something that I really enjoy and that I really believe is like the valuable thing that we are doing as academics. Like, it's not necessarily the research that we put out from our labs that is our lasting impact. Although, if we happen to make a really incredible discovery that's going to like change the energy economy of the world, that would be fantastic, right? That would be so cool. But that those are going to be the exception rather than the rule, and that the main impact that we are really making is the training and mentoring of students who are then going to go out and do their own science in the world. And so it was through doing those informational interviews that I really came to realize that that was the piece of academia that was important to me and that I did not want to give up. And so that's when I said, okay, I'm gonna apply for academic jobs. And I think if I hadn't gotten an academic job, that would have been fine. I would have been happy, as I said, going and working in industry. But I'm really glad that I've been able to find a position where I do get to engage in teaching and mentoring as a really, big piece of what I do. So
yeah, I think that's the most rewarding part for me as well. It's
the
mentorship and the teach. Like you just. It's just the most rewarding part. It's hard to explain. Like, and then you send them out and they do great things, and it's like, you help hopefully spark some of that.
So I was saying earlier that I did this mass media fellowship, right? And I said we should come back to that because, we were talking about it in the context of career exploration. But one of the other things that I really brought back from that fellowship experience was the importance of understanding how to communicate with different audiences and how to tell a good story scientifically, right? And so, one of the first pieces that I wrote the summer that I was working for the Milwaukee Journal-Sentinel was a little blog post. I think it was like 300 words long. And it was about a news article talking about loggerhead turtles that were mistaking plastic bags in the ocean for, I think, their food sources. It's been a long time. I don't really remember the details. But I turned in a draft of this piece to my editor, and it came back with a whole bunch of comments on it that were like, loggerhead turtles, ? How big? Where do they live? Etc. Right? And so I had just gone right into the science pieces of the story without giving any of the context about why readers in Milwaukee, Wisconsin should care about this topic, right? And, a number of other interactions that summer really kind of drove that point home that you have to get people to care about what you're doing before you can give them a bunch of information, or they're just going to tune out, right? And so that's something that I brought back with me to my academic work. That, and also understanding, what is the knowledge that my audience has, what vocabulary they're going to be familiar with versus not familiar with, what do I need to explain, what are they already going to know, what are they going to find interesting, and using that to inform the way that you put together talks, but also scientific papers, right? And I think one of the things that I've been on a bit of a tear about with my own students is the importance of really understanding the scientific narrative that you're trying to tell, right? It's not just I took a bunch of data, here's all my data, right? That's not what we should be doing when we're writing a paper or giving a presentation. We should be constructing a scientific narrative where we say, this is the big picture problem that we're trying to address, and here's the small piece that we're working on and why you should care about it, and then let me tell you about what we learned, right? And one of the most powerful sort of frameworks that I've come across for thinking about that narrative construction is in a book by a guy named Randy Olson called Houston, We Have a Narrative. And so the author is a PhD scientist who became later in his career a Hollywood screenwriter. And so he wrote this book that's about the importance for scientists of understanding how to construct narratives, sort of Hollywood style, and be able to use those when we're putting together particularly scientific papers. And one of the really powerful tools that kind of just goes throughout this book is this idea of what he refers to as an and, but, therefore narrative structure. So we start by saying, we know X and we know Y, but there's this challenge Z, therefore we need to do A, B, C. Right? And that sounds like such a simple structure, but once you start looking for it and once you start actually trying to apply it in your own science writing, it can really, really help with constructing a story that people care about, a story that will get people to read the rest of your introduction, read the rest of your paper, actually look at the data that you took and learn something from it. And so I can't do justice to that entire book in the time frame of a podcast, but especially for any students who are thinking about how do I become better at kind of writing engaging science writing, I highly recommend checking it out. And it kind of also connects back to that point I was making earlier about maintaining a sense of the big picture, because you also need to have that big picture to be able to tell that narrative and convince people about why they care about your little sub-problem that you're poking out on the boundaries of human knowledge. So, yeah.
No, that's amazing. It's you're the second guest to suggest books. I think I need to start a book club.
Yeah.
And a Rad Lab book club, because I think maybe I'll start forcing my students to read all these too. I think these are that sounds like a great book. Hopefully it's not too long.
No, it's pretty, it's not super long, and it's pretty engaging. Like, he's pretty funny, and he has a lot of just good examples throughout this book of, here's the really dry version, and here's what happens if we rewrite it in this sort of and, but, therefore format. And it's not even that the rewritten version is like funny or unprofessional or anything. It's just taking the professional writing and turning it into this successful narrative structure, which then makes it more engaging. And so it's something that we, in my research group's group meetings, we periodically do what we refer to as a writer's workshop group meeting, where every student in the group brings 2 pages of something that they're working on, and we pass it around in small groups, and we essentially peer review each other's writing. And this narrative structure piece is something that almost every time somebody brings a draft of an introduction for either a paper or, their second year oral exam, they have to write a document for it. It's almost always something we end up discussing, and it almost always makes the introduction tighter and more interesting once they've kind of revised with that in mind. So
yeah. Do you make all your students read this book, or?
We don't usually read the whole thing, but I do sometimes hand out excerpts of it. I do have a copy in my office that I loan out sometimes, but for the most part, we kind of just discuss it and talk about how it applies to the specific piece of writing that they're working on.
Gotcha. I might make my students
it is a fun book, so I enjoyed reading it. So, yeah.
It sounds like my kind of book. It sounds like
yeah.
So yeah, I'll definitely take a look at that, and I probably will end up making my students read it. No, that's amazing. So we've talked a lot about work and what you do day to day. Well, let's talk about the things that, I guess, keep you going. Mm-hmm. So what kind of hobbies are you into?
Okay, so I have way too many hobbies, like way, way, way too many hobbies. I would say that when I am not in the lab, the things that you can most often find me doing are walking my dog. I couldn't. It was hard to have a dog in grad school because, it's hard to manage time-wise. But my partner and I have a dog, and we live right next to a really big park. And it's just so nice to have this reason to get out and walk in the park for an hour or two every day, right? And dog gets us up at the same time every morning, and then we go take him for a walk. And it's just a really nice way to start the day. But aside from walking my dog in the park, the 2 places you're most likely to find me are either at the ballet studio. So I've been dancing since I was about 5 years old. And it's one of those things that I've just stuck with for a really long time because it's not only good exercise, but it's also a really good chance to just do something creative with people who have nothing to do with my day job, right? And it's a good chance to meet people. One of the things that is challenging as a professional scientist is you often end up moving to a city where you don't know anybody. And so finding friends can sometimes be hard as an adult, right? And so ballet classes have been where I've met probably my best friends in Pittsburgh that, none of them are scientists, and that's great. I love my science colleagues, but sometimes I need to do things that don't have anything to do with science. But then I also really like to sew. So if you have ever watched the Magic School Bus, and particularly the original Magic School Bus, the teacher, Miss Frizzle, has all of these great science-themed outfits, and I am slowly in the process of turning myself into Miss Frizzle. No, I'm joking a little bit, but I really like to sew, and so I have one of the things I love about sewing my own clothes is that I can make things that fit me correctly, which is hard sometimes with store-bought stuff, but I can also make them in really fun patterns. And so I've made like shirts that have atomic orbitals on them and chemistry glassware, and it's a fun way to kind of express a little bit of my science nerdiness. I tend to wear those when I'm teaching. Gets the students to smile. So, yeah, usually out with the dog, taking ballet class or sewing, or sometimes playing board games with my partner. So we have a good time.
What's your favorite board game?
Oh, that's really hard. Oh man, there's so many that I like. Okay, so if I had to pick a single favorite, I think I might have to pick Ticket to Ride.
Ticket to Ride. Okay,
yeah, do you know this game?
I think so, yeah.
Okay.
Where you're trying to make the train tracks?
Yeah. So Ticket to Ride is this game where there's a map, and then there are these train routes connecting different cities on the map. And then you're trying to play train routes to connect the cities for your tickets, which will get you points. But there are ways that other players can block you, and so it can be kind of competitive. But I like Ticket to Ride because I feel like it has a lot of really good replay value, and it's one that I don't feel like the setup is so difficult that it's hard to teach new people. It's one that we can kind of just pull out and play, but it also doesn't feel like it gets boring, right? Playing it over and over. But recently, I wouldn't say this is my favorite game, but one that we've just been having a lot of fun playing recently, is this game. Oh man, I can't remember the name of the game now. It's escaping me, but it's a game centered around mushrooms in a forest. And you're trying to grow trees that will then support your mushroom ecosystem in a forest. And it's a really clever game in terms of how it's set up, and we've been having fun playing that one too. So
that's awesome.
If I can remember the name of it, I'll send it to you.
Sounds great, because we some of the faculty here, we do board game nights and things like that. So we're trying to always find different board games and things like that. Have you ever played Carcassonne before?
Oh yes, I have.
Okay, I was if you haven't played that, that's something you really do.
Yeah, no, I really like Carcassonne, and Carcassonne has so many expansion games. I had this friend in grad school, shout out to Joe Yeager, he's a lab instructor at Smith College, who liked to play, I think what we referred to as Mega Carc, where we would just put together all of the Carcassonne expansions that we had, and it would turn into this hours and hours and hours long game where you're kind of building up the board as you go, and it would just take up the entire table. So yeah, I haven't done that. I haven't played it in a long time because I think it's one that plays better with more than two people. But I do really like Carcassonne, and my favorite expansion is the Princess and the Dragon expansion because it's really fun. There's a dragon that moves around the board, and then the dragon can eat people's meeples.
Oh man,
and
that's great.
It doesn't work super well with two people because then you're just kind of going back and forth moving the dragon. But when you have multiple people, you can cause a lot of chaos with the dragon really quickly. So if you like Kark and you have not played the Princess and the Dragon expansion, I highly recommend that.
No, that's now I need to go buy some. I need to go on Amazon and get it because we're looking for different ones to try, and I think that would be a great one for us to try. Yeah, because another one for like if you have a big group of people is called Saboteur. Have you ever played that?
Yeah, I like Saboteur.
Oh, so you know all the great ones.
Yeah.
So, no, I love Saboteur. That's a great one. I learned that I tried to do. I didn't want to look at my card to see if I was like a saboteur or not, and I just try to play it kind of neutral and just like try to keep the game even, and it just turns into everyone hating you. So and then you get disappointed because you often end up you think you know what you are, and then you don't, and then you don't, and then don't try that.
Our department's grad student group also occasionally has board game nights just as a fun social thing to do with other students in the department. They get pizza and stuff, but one of the really popular games when we do that is Codenames. And so that's just a really fantastic, I don't think it would be great for just like a board game group, but especially as a party game when you have a whole bunch of students getting together, Codenames is really, really fun. Yeah. So that one is a staple of our department game nights.
That's awesome. Yeah. That's awesome. Yeah. Well, thank you for taking the time to speak with me.
For sure.
I will make sure send me all of the links and all the things we discussed. They'll be in the description. So if you're interested about this and you're listening, you want to check some of those things out, please look in the description, check all of them out. And once again, thank you for being on here and talking with us.
Yeah, thanks very much for having me. It was a lot of fun.